Okay, we're going to go over some more derivative examples for you guys. Some examples I promised to give you, some additional examples. So let's try some more here. Determine y prime or simply the derivative, right? So we're going to try one here. Let's say, we could just call it example. They give you the function y is maybe 3 secant x plus cotangent x. Okay. So y prime will be the derivative of 3 secant plus cotangent. So remember, use your operator notation. So this will be 3 secant plus the derivative of cotangent. So you can pull out your 3. And you have secant plus the derivative of cotangent. So now we have to know the derivative of secant here. And that's going to be secant tangent. Derivative of cotangent is minus cosecant squared. So put this all together. 3 secant tangent plus the minus cosecant. So you end up with 3 secant tangent minus cosecant squared. So there's your derivative. Okay, so here's another example of what to do. Then maybe you're going to say, let y be 1 plus, how about this? X cosine x. Okay. Y prime, the derivative of 1 plus x cosine x by properties. Derivative of 1 x cosine x. Here, we're going to have the product rule. So let's kind of write that down here. So by product rule, we get x derivative of cosecant plus cosecant derivative of x. So maybe let's just move everything over here. And cut this part here too. Okay. Derivative of cosine here will be minus sine, and derivative of x is 1. So altogether, don't forget the derivative of your constant will be 0. So, we're answering everything here. We get minus x sine x plus cosine x. So here's your derivative. Anyway, here's going to be the product rule. Okay. So let's look at another example. And how about this? 1 plus sine x over x plus cosine x. Okay. So in this one, we take the derivative, and as you can see, it's going to be quotient rule. So by quotient rule, here's what you're going to do. X plus cosine x squared, x plus cosine x, derivative of 1 plus sine x, minus 1 plus sine x, derivative of x plus cosine x. And we're running out of space there, so let's kind of make some space. Oops. And here we go. X plus cosine x. Okay. So the derivative here of 1 plus sine x is really the derivative of sine, which will be cosine. And over here we have the derivative of x plus cosine x. So we're going to take the property where it's a derivative of a sum. So the derivative of x is 1, and the derivative of cosine is minus sine. So take a look at this, and you'll get x plus cosine x times cosine minus 1 plus sine x times 1 minus sine x. So everything here is over x plus cosine x squared. So at this point, what you do is use algebra in the numerator there and see what you can actually simplify. So distributive property x cosine x plus cosine x. So here's what you have here. And then this is minus 1 minus sine squared x. Everything over x plus cosine x squared. So we get x cosine x plus cosine minus 1 plus sine squared x. And it looks like there's nothing really more we can do. Let me double check, see if we did everything okay. You know, it looks like nothing else can, is going to cancel here. Let's see. X cosine x, we got that, plus cosine, oh, there's a cosine squared. I apologize. There is some simplification here. Cosine squared here, ladies and gentlemen. Yeah. And here's what I want to say. If you guys remember here, take a look at this. Cosine squared plus sine squared is actually 1. Okay, so you have these two terms. Let's write this down. We have cosine squared plus sine squared is 1, Pythagorean identity, and that's going to cancel with this minus 1. So your answer is going to be y prime x cosine x over x plus cosine x squared. So ladies and gentlemen, there was simplification. That's why I double checked this, and that's good. And so you use a Pythagorean identity. This simplifies things, and you're going to need to be able to simplify some of these by using some algebra and trig identities, because when you deal with applications, they're going to have you really do some work there. Right? We're going to see some of that. So let's give you another. How about this one? So y is tangent x minus 1 over secant x. So y prime will be d dx tangent x minus 1 over secant and quotient rule. And I actually started doing quotient rule. So secant squared x, secant x, derivative of that numerator. Tangent minus 1 minus tangent minus 1, derivative of secant. And I really hate when I run out of space. Anyway, let's clean that up. Secant. Derivative of tangent minus 1, this is secant squared. Secant tangent. Secant. Now, notice what this is. Secant times secant squared minus tangent minus 1 secant tangent. Now, this kind of looks like something we might have did earlier today. I hope it's not. Hope it's not the same one. Secant cube minus, now I'm going to distribute here. It's kind of, I think we did this earlier. This is going to be, it looks familiar. Yeah, it's secant tangent squared minus secant tangent over secant squared. So we get that secant cube minus secant tangent squared plus secant tangent. And that's over that secant squared. And I think this morning we factored out the secant. Yeah, this is very familiar. So we get secant squared minus tangent squared plus tangent over that secant squared. So secant goes away, and you're left with secant squared minus that tangent squared plus tangent over secant. Now, secant squared minus tangent squared, if you remember what we did this morning, let's try to find that one. Right, I think it's here. Secant squared minus tangent squared. I want you guys, there we go. Yeah, that's what it is. We use this identity here, right, this morning. So secant squared minus tangent squared. So we can actually do something like this. If secant squared, it's going to be 1. Let me point that out to you. Let me do something like this. If I translate and move that term, that means secant squared minus tangent squared is really 1. So that's the identity we want to use. So if you ever see secant squared minus tangent squared, we know that's 1. So this is an identity. And we did see that this morning. So y prime will be 1 plus tangent over, secant. Pretty interesting. I think we did talk about that one in great detail. Let me do something here. So y is x, sine x, cosine x. I know your book has something kind of similar. Let's see what we get now. So we're going to use product rule, ladies and gentlemen. Let me show you how something like this will work. Okay, by product rule. Here's what I want to do. It's up to you. I'm gonna look at this first two as a single function, and this last one as a different function. So you're going to see how product rule works here. You pull out the first function as if it were a constant, and you differentiate the next function. Then pull out that function and differentiate the first function. Yeah, there we go. Sorry. So, constant in green. There we go. And then you have the orange here. Okay, so here's your product rule. Now, derivative of cosine is minus sine. Now, derivative of x, sine x, again, product rule. So this will be x. Let's change that color. X, derivative of sine, plus sine derivative of my x. Derivative of sine is cosine, derivative of x is 1. So let's put this all together here. So we got product rule here. So we have x sine x times that minus sine x. We're starting here on the top. Multiply those two terms. Plus cosine x times that cosine x times x cosine x plus sine x. We're going to take this x. Oh, don't forget there was a cosine first. And we get this x cosine x plus sine x. Okay. So I get minus x sine squared x plus x cosine squared x. And then it looks like it's just plus a cosine sine. And even if you factored out that, x, it doesn't do anything for you. You don't have an identity there, so you're gonna leave it as it is here. Okay. So that's kind of like an example in your book, I think. Okay, so you got some good examples there, and then I'm going to say to you, let's find some real ones. Find the equation of the tangent line to the curve at the point. So this is the equation to the tangent line to the curve at the indicated point. So let's get that curve again. So I'm going to see here we have 1 plus x cosine x, and the point they give us is 0, 1. Okay. All right, just checking a few things here. Go. Okay. All right, so ladies and gentlemen, of course, you know by now that this is y minus y1 is m tangent x minus x1. So here's my x and y coordinate. y1 is 1, x1 is 0. M tangent is the derivative of that function evaluated at 0. So we can call that y prime is 0 here. So we need that derivative. So y prime will be the derivative of 1 plus x cosine x. Product rule, ladies and gentlemen. Right, first function, second function. So you're going to pull out the 1 plus x. You're going to differentiate cosine plus cosine, and you're going to differentiate the 1 plus x. Derivative of cosine is minus sine. Derivative of 1 plus x is 1. So you end up with x plus 1, and that's a minus sine x plus that cosine x, ladies and gentlemen. Okay, so here's y prime. Now we have to evaluate that at x is 0. So that gives us y prime of 0, negative. Plug in a 0 now wherever there's an x, right? So here's a 0 goes here, 0 goes here, 0 goes here. So you get 0 plus 1 sine 0 plus cosine 0. And 0 plus 1 is 1, so that's minus, let's write down the value of sine here, by the way. Sine of 0 is 0, and then cosine of 0 is 1. So we get now minus 1 times 0 plus 1, or y prime at 0 is really the value 1. So we replace this y prime 0 with a 1 here. So here's what you get. Y minus 1 is 1 times x minus 0. Or y minus 1 is simply x, which means y is x plus 1. Okay. I really hope we didn't do this one this morning either. Did we do that one too? Let's double check. Do we do that one? Oh, that's x minus 1. No, that's a different function this morning. Okay. Ah, very similar, huh? All right. Okay. And we do the same kind of thing here, but this time the function is 1 over cosine x plus sine x. And this will be at also 0, 1. So let's double check. Let's hope we didn't do that one this morning. No. No, I think I made it up this morning, that function. Which is fine. Okay. So you guys know already, this will be y minus y1 m times x minus x1, your x and y coordinate, your first and only point. So 1 and 0. And this is really m tangent, so this will be y prime at 0 again. Okay, so y prime will be the derivative of 1 over sine x plus cosine x. Or cosine x plus sine, it doesn't matter. And quotient rule. I'm going to start way out here, just in case. You square the denominator. And differentiate the numerator. Minus the numerator. Derivative of the denominator. So derivative of 1 is 0. Derivative of cosine plus sine, derivative of cosine is minus sine. Derivative of sine is cosine. Okay. So altogether, here's what you'll get. Don't forget, this is going to be a function squared times 0 will be 0, so that's gone. And this will be minus 1 times sine. That'll be sine x, and that'll be minus here, cosine x. So we're going to take negative 1, multiply it to a negative sine x, will be positive, and then a negative times a positive is negative. So, okay. Over cosine x plus sine x squared. So this is y prime, and if I evaluate this at x is 0, we get y prime of 0 is going to be sine 0 minus cosine 0 over cosine 0 plus sine 0 squared. Now, sine 0 is going to give you 0. Cosine 0 is going to give you 1. 1 and 0. Y prime 0 becomes minus 1 over 1 plus 0 squared. And so that looks like my y prime of 0 is a negative 1 over 1 squared, or that y prime is 1 at 0. We know m tangent here is 1. It's negative, I apologize. All right, negative 1. So we're going to go back here, and you say, okay, you are negative 1. Ladies and gentlemen. So we're going to go through some of the things we did today. So y minus 1 is negative 1, x minus 0. Y minus 1 is negative x, and y is negative x plus 1. Here you go. And there you are, ladies and gentlemen, negative x plus 1. Okay. Another example of the equation of the line, tangent to the curve at a point. They're going to give you now this curve. Y is secant x minus 2 cosine x at the point. Now, it's good to not have 0, 1 anymore. Pi over 3 comma 1. So this is the same question. Y minus y1 is m tangent x minus x1. Here's your one and only point. So you're going to plug in for x, pi over 3. You're going to plug in for y1. So you just need this m tangent here. And we have to differentiate, right? So we need that y prime. d dx secant minus 2 cosine. So properties of derivatives. The derivative of a secant minus 2 derivative of cosine. So just go through those properties. Derivative of secant tangent. Derivative of cosine minus sine. So that your y prime will become secant tangent plus 2 sine. Okay, so double check this. And now we have to find what that is at pi over 3. So you get y prime of pi over 3 is secant pi over 3 tangent pi over 3 plus 2 sine of pi over 3. Okay. We need to know what this is. Now remember, from trig, pi over 3 is 60 degrees. So these are all really, if you want to think of it this way, this is sine, secant, this is secant tangent of, and sine is 60 degrees. So this is kind of, you can think of in some way as being in a geometry course. You go, what do you mean? Yeah, this is actually geometry. It's found in trig as well. Here's what I mean by that. Here's my triangle. It's supposed to be equilateral. Let me try to make an equilateral triangle. If I can. Right, so this is my 60 degrees. 60 degrees. We bisect that 60 degree. This becomes now 30. And typically we say 2. This whole thing is 2, but this will mean my sides are 1 because we bisected, and this was square root of 3. So if I'm looking at this triangle here now, I'm going to change this here. Here's my focus now. That's my right triangle. So I'm going to use some definitions. I'm going to say cosine of 60 degrees. Remember the definition of cosine. It's adjacent, which is the adjacent side, 1 over the hypotenuse 2. Special triangle. Which means secant of 60 is 2. So this value up here is 2. Now we need sine here. Say sine of 60 degrees. Well, sine of 60 is opposite square root of 3 over hypotenuse 2. So this is square root of 3 over 2, ladies and gentlemen. We just need tangent now. You say, what's tangent of 60? Well, tangent of 60 degrees is opposite. Remember, this is my 60 degree angle here. It's opposite over adjacent, square root of 3 over 1. So I replace the tangent with square root of 3 over 1, which is just square root of 3. So here's my y prime. It's 2 square root of 3. Right? So we're looking up here. 2 square root of 3 plus 2 square root of 3 over 2. Y prime is 2 square root of 3 plus another square root of 3. So y prime is 3 square root of 3, ladies and gentlemen. Pretty nice question. So this is my slope, 3 square root of 3. So you say, do I have to go back up here and plug that in? Yes, you do. 3 square root of 3. So you get y minus 1. We're going to copy this. I'm going to paste it. So y minus 1, 3 square root of 3, x minus pi over 3. So distribute 3 square root of 3x minus, looks like the square root of 3 pi only if I distribute. Yeah, because the 3's cancel. So add your 1 to both sides, and ladies and gentlemen, that equation is 3 square root of 3x minus the square root of 3 pi plus 1. And there you go. It's a pretty nice question here, ladies and gentlemen. So, you know, that's the same nature kind of question. And then another example. I'm going to change the example here. Here's what I'm going to say for this one. Find the points on the curve. For the horizontal tangents. So it's the horizontal tangent question. Y equals cosine x over 2 plus sine x. Now remember, horizontal tangents happen when the slope of the tangent line is 0. So essentially we have to find the derivative of this function and set it equal to 0 and solve for x. So looks like we have a quotient rule question. So 2 plus sine x squared. Quotient rule. So we get the derivative of cosine minus cosine derivative of 2 plus sine x. Derivative of cosine minus sine. Derivative of sine is cosine. Two plus sine x times minus sine x minus cosine x times cosine x. Everything over 2 plus sine x squared. So we're going to get, looks like, let's distribute negative 2 sine x minus sine squared x minus cosine squared x, 2 plus sine x squared. Negative 2 sine x minus, in parentheses, sine squared x plus cosine squared x over 2 plus sine x squared. And then this value here we know is 1. So we get minus 2 sine x minus 1 over 2 plus sine x squared. So here's our derivative, ladies and gentlemen, our m tangent. So we set this equal to 0. So we have minus 2 sine x minus 1, everything over 2 plus sine x squared, and then that's 0. Now remember what we've been saying, if you ever have a fraction and the fraction equals 0 here, that means my numerator is 0. So that means negative 2 sine x minus 1 is 0, or we can simply say sine x is a positive 1/2. And you say, well, how did you get that? I just solved for sine. Right? I got sine by itself. I solved for that. So we add 1 to both sides. And actually, I think it's negative. Yeah. Add 1, right? You get negative 2. Sine is 1. So there you go. So I have this equation here. Now, I'm going to have to be very careful here. I'm going to have to read what this says. Notice they didn't give me an interval. They didn't restrict the domain of the function. This is over all real numbers. That's my domain. Okay, so the domain is all real numbers because they didn't restrict it like maybe from 0 to 2 pi, right? They didn't do that. So they're asking for a general solution. This is cosine plus 2 over sine. So I want to show you guys cosine plus 2 over sine here. If we go to Desmos, these are all other examples. So cosine, we say, to show you what I'm talking about, cosine x divided by, in parentheses, I think it's 2 plus sine, is that right? All right, I double check that, see if that's this function. Here's my point to you. This is the curve. And this curve is periodic, by the way. Okay, it's periodic, meaning the behavior repeats after a certain period, right? You have a certain period where your length of one cycle in which this behavior simply repeats this function. It's periodic behavior, and there's locations on this curve where you have horizontal tangents, right? Pretty much at the top of a hill and out a valley, horizontal tangent. So I can see one being something like maybe over here. I don't know. Can I touch the curve? All right, maybe there. Horizontal tangent, and then in a valley somewhere like over here maybe. Okay, so you guys know, like maybe somewhere there. I guess it's a reason why they let you locate some points, not every point. All right, whatever, can't get that point. So that's my point. It's a periodic behavior, and this is over the real number line. So I have to solve this for x. And the solution here, when you solve for x, remember you go through that whole, all students take calculus, meaning quadrant 1, quadrant 2, quadrant 3, quadrant 4, all trig functions are positive. All students take calculus. Here's my point. For sine to be negative, we're talking an angle in quadrant 2 and 3 and 4. This is the quadrant where your sine function is negative. So this is where this angle lives, from 0 to 2 pi, of course, right, on your unit circle. So we need two angles. Now you have to go to the reference angle. You say reference angle, yeah. Sine of theta or x are really quadrant 1. You could use your reference angle, by the way, in blue. Let's color this. This is your reference quadrant. So I can say I need to solve this for x for the positive value. And remember the definition, sine opposite over hypotenuse, right? So you get that right triangle. And we say things like the opposite side is 1, hypotenuse is 2. And you start to say, oh, I know what special triangle this might be. This is 1, this is 2, this is square root of 3. You might say, oh, 60, this was bisect. This is 30 degrees. So the angle here, or the solution here, is that 30-degree angle for x. So we can say, x is 30 degrees, but this is in radians. So x is pi over 6. And we have to be careful here. That's where you have a positive value. 30 degrees. So let me draw these lines here. Yeah, I guess it doesn't do that. Here's this. I'm going to try to draw a 30-degree angle here. So here's the reference angle, 30 degrees, ladies and gentlemen. We need the quadrant 3 angle. So you say, how do I get this if my reference angle, if this is 30, right? You guys remember how to get that reference angle? We already have it, pi over 6, or 30 degrees. So x will be, as an angle, looks like 180 plus 30, 210 degrees. Or you say x will be pi plus pi over 6, which gives you, 6 pi over 6 And I'll say x will be 7 pi over 6, ladies and gentlemen. Now that's only one solution from 0 to 2 pi. So I'll call that x1. That's the quadrant 3 angle solution. So remember, we also have a quadrant 4 angle solution. And if this also measures 30 degrees, 360 minus 30 is the quadrant 4. So x will be 360 minus 30, or x will be 330 degrees. So you can say, is that the same as taking 2 pi minus pi over 6? It is. Don't forget to multiply the top and bottom by 6. x2 will be 12 pi over 6 minus pi over 6. x2 is 11 pi over 6. So these are the solutions I'm looking at in quadrant 3 and quadrant 4. Those angles. Okay, now you say, okay, Mr. Judge, but this is periodic. They didn't restrict my domain. And I'll say, I know you need the general solution, which is now to do the following. Add the n revolution portion, 2n pi. And for the other solution, add 2n pi. So this is the general solution over all real numbers. Since your domain is all real numbers, the domain is not restricted. They didn't say 0 to 2 pi, so that's not the particular solution. These are general solutions. So these are actually trig equations, ladies and gentlemen. So in some ways, you solve the trig equation. And notice some of these answers here. And, like 7 pi over 6 and 11 pi over 6. If I go back to Desmos, remember, I think for one of them, I try to find a location on the curve if it lets me. Yeah, it did. See this? That's the location of your horizontal tangent, 7 pi over 6, at the bottom of your hill. Kind of like in a valley, at the exact location in that valley. And then up here, notice this point here. See if we can do the same. Okay, what is the address? 11 pi over 6. So that's at the top of your hill. So this is the locations where you'll have these horizontal tangents. And, as you can see, this is periodic. This is why you keep adding a multiple of 2 pi for both solutions. You have to keep adding a multiple of 2 pi. You can subtract multiples of 2 pi from both solutions because you're going in the other direction too. So you guys can see this somewhere over here. Did I touch it? There. Negative 5 pi over 6 is another location because it's at the bottom of a hill. So at the exact bottom of the hill where you'll have a horizontal tangent, negative 5 pi over 6. And then at the top of this hill, if we can find it visually, there we go. We just did negative 13 pi over 6. So you keep using values of n for the general solution here, where n is an integer. Okay, n is an integer. And this is n. This is that n value they're talking about here. N. So that's your general solution. N is an integer. N is all these values. And then that comes from your solving a real trig equation by definition. There's your integer values. Z is a set of all integers. So you can change those values of n, and you get all these locations. So this curve is periodic. So I'm just going to say this. We just found locations here. Okay. We found the x values. You say, how would I find the y values? We'll plug in these x values in general, and you get these locations here. So that's another example of finding horizontal tangents with trig functions. Okay, and let me double check here if I want to do something like this. Yeah, you got vertical motion. You got motion of a really, it's not a particle. maybe x is 8 sine t. You got what's called simple harmonic motion. Motion's periodic. You got the sine curve. And I don't know, is this vertical? I guess they want you to define. This is a simple harmonic motion. X is the position on the x axis in centimeters, and then t is a unit of time. So t is maybe in seconds. So just kind of highlight some things so we don't get confused. This is simple harmonic motion. It's actually going to be left and right motion, kind of like your book. You know, if you want to draw a picture, it's the very famous, you know, mass string, where you move this, push this mass to the right or the left. I'm going to draw the real number line now here. Okay, so here's my kind of my x-axis. And it's your position here. X is 0. And, you know, you can push that spring in and let it go, and it's supposed to oscillate forever. Or you can pull it to the right, let it go. You know, you do different things. So here's kind of a question. And they say, what's the velocity function? So they're going to say, determine the velocity function. Let's get you guys back. So determine the velocity function. It's a rate of change question. They want x prime t, which is the derivative with respect to t of 8 sine t. That's the derivative of your position function. Okay, so x sine t is the position function. If you take its derivative, that's dx dt, by the way. That's the change in x over the change in time. So use properties 8, pull out the constant. Derivative of sine here, ladies and gentlemen, is cosine. So that x prime t, or dx dt, is 8 cosine t. There we go. So here's my position function. And they're going to say, determine the velocity at t equals 2 pi over 3. So you can even say, we change the color, this is my v of t. So you say v of 2 pi over 3 will be 8 cosine 2 pi over 3. So you might say, well, what's cosine of 2 pi over 3? Well, 2 pi over 3 is 60, so this is 120 degrees, right? So how I deduce this using trig, right? We're going to use the all students take calculus. Go through that detail. 120 degrees is over here. So if we say this is 120, this is 60 degrees. This is our reference angle. So I thought I wrote down somewhere cosine of 60. So we need cosine of 60, the reference angle. I think it's up here, maybe somewhere, cosine of 60. At least we have the triangle. Cosine, no. Well, anyway, we can find cosine. Cosine of 60, ladies and gentlemen, use the definition. Cosine, is it cosine of 60 we have to find? It's adjacent over hypotenuse. It's 1/2. Cosine. Okay, so this is 1/2 here. But all students take calculus. And what that means is in quadrant 2, where this angle lives, 120 lives, is in quadrant 2, which means sine's positive, and that implies that our cosine will be negative. So here's how that works. This means cosine of 120 degrees is actually minus 1/2. That's why they call it the reference angle. It's the same answer, but it differs by sign. By that system, all students take calculus. So cosine of 120 is negative 1/2. So anyway, I guess that's what they wanted to find. I'm sorry. This is my velocity. So v at 2 pi over 3 is negative 1/2. That's what that means. And I want you to note the physical meaning of what's happening. If I ask you guys, what direction is the particle moving at this time? Right? Since my velocity is negative, you got negative velocity, that means the particle is moving in the negative direction horizontally to the left. Or sometimes they say backwards, whatever. It's moving to the left because the velocity is negative, right? And then another note, or we say, by the way, what is the speed of the mass at t is 2 pi over 3. So what's the speed now? We say speed here is the absolute value of the velocity. Absolute value of negative 1/2. So my speed is actually 1/2. And I think they use the distance to be what units? Centimeters. Okay, so centimeters here. And so my speed will be centimeters per second. And that's my speed. There it is, ladies and gentlemen. You got the direction of the particle, and then you have its speed. So, I don't know. I think that's good for now, for today. Give you guys a little bit of extra examples today, and you take a look at it, and I'll upload it to you as soon as possible, and I'll remind you guys of this in Canvas and also in lecture tomorrow. So take a look at it. It looks good. Have a great day.